I'm Natalie Collina. This is my excellent friend and collaborator, Eshwar, and we are very excited to present our work on Pareto-Optimal algorithms for learning in games. And this is joint work with our excellent colleague, John Schneide, who is there in the audience. Hi, John.
Okay, so completely consistent with the place we are thinking of agents using algorithms to make decisions. And we are thinking of agents making these decisions in strategic settings, in particular, particularly in the context of repeated strategic interactions, the standard examples being repeated auctions, repeated pricing games, repeated routing games, whatever is your favorite class of games. And we are sort of thinking of these finite action games, finitely repeated. You can see like the matrices where the agents choose their actions. And they are going to play using algorithms that look at the history of play and decide what to do in the next round. So naturally, this means that these algorithms can be adaptive to how the other players, other agents make decisions in this game. Of course, they can be dynamic over time. And we are going to analyze a very special, very clean, special case of this formulation. So it's a game with two agents whom we call the learner and the optimizer for reasons that will become apparent. And it's an asymmetric game. So there is a fundamental difference between the learner and the optimizer, which I'll clarify in a moment. So both agents start with some private information about their payoff matrices and encode their preferences on this game that they are playing repeatedly. And the learner, true to form, picks a learning algorithm that makes decisions for them. So it looks at the history of play. Presumably, since it knows itself, it knows their own history of play. So it looks at the history of play of the other player, the optimizer, and decides what action to pick in the next round of play. And throughout this talk, whenever we say action, we really mean a distribution over the finite actions that each of the players has in their action space. And for simplicity's sake, we are going to assume that these distributions are going to be visible to both players at the end of each round. Okay, but here's where the interesting element in the problem arrives. So the learner looks, at their own preferences, looks at this game from their perspective and decides what learning algorithm they're going to play. And in fact, they are going to publicly announce and commit to playing this learning algorithm. So they tell the optimizer, hey, this is exactly how I'm going to make decisions based on the history of play so far. And now something interesting is going to happen. The optimizer is a dastardly character who looks at this learning algorithm, who is, of course, aware of what they like in this game. And they come up with a sequence of actions tailored at maximizing the total payoff that they are getting from this repeated game. And this is really this paradigm is really at the heart of this work. And I urge you to take a moment and think hard about this. So here you have an optimizer who's aware of the learner's algorithm, and they're coming up with a sequence of actions to maximize their payoff. Like, think of your favorite game, think of your favorite learning algorithm. Maybe it's a repeated pricing game. Maybe your favorite algorithm is multiplicative weights. How would you as an optimizer play to maximize your payoff in this game? If it's a zero-sum game, easy enough. It is not a zero-sum game, interesting things can happen. It's a very interesting problem from control. A lot of our paper is about understanding how these test responses work and what trajectories of plays they induce in the resulting sort of gameplay. Okay, so this is sort of the paradigm that you're operating in. So what's the problem you're trying to solve? So now the learner does like one more level of thinking and asks themselves, okay, I know whatever algorithm I pick, the optimizer is going to best respond to it. So what algorithm should I pick to maximize my own payoff in the resulting gameplay? Okay, so I'm going to tell you about a special case of the problem to tell you why the problem isn't quite well formulated yet. And the special case is when the learner starts with full knowledge, not only of their own preferences, but also of the preferences of the optimizer. And for those of you who are familiar with this is just a Stackelberg equilibrium problem, but in the repeated game instead of a static game. Okay, however, this is not the subject of this talk because this is a paper that we wrote last year to sort of efficiently solve this problem. It's already a non-trivial problem, by the way, but you can see that this is a well-defined problem because whenever you commit to an algorithm, since you know exactly well, in theory, you know exactly how the optimizer is going to best respond and what's going to happen and what payoff you're going to get. Okay, but let's go back to our original problem where you only start with knowledge of your own payoffs. You don't know the nature of the optimizer at the start. And this means that depending on who turns up to play against you, the outcomes are going to be different. The payoffs are going to be different. So it's not clear what we mean when we ask for a learner algorithm that maximizes the learner's payoff in the resulting play. Our paper is about sort of dealing with this issue. So what can we expect to do in this setup? First of all, I want to point you to the first line on the slide, which says like optimistic. Can we come up with a single learning algorithm that somehow gives you the optimal value against every optimizer had you known the optimizer? It's not very hard to see that such a thing does not exist. There is no silver bullet for this problem. Like you could just think, for a simple example, what you would commit to in a zero-sum game is in fact very different from what you would commit to in a game like Repeater Prisoner's Dilemma or like any non-zero-sum game you could effectively think of. You could be pessimistic as the learner and just play within yourself and get your safety value of the game. But in this community, we have better standards, and the better standard is typically no regret, which we have been talking about in the past 2 talks. So the standard benchmark is that you want to have an in hindsight guarantee that says that whatever happens, my payoff should be comparable to that of playing the best fixed action in hindsight. What we ask for, however, is something strictly stronger. So we are going to ask, and we'll tell you why it's strict. We are going to ask for not just no regret, which is a very reasonable consistency property of an algorithm, but we're also going to ask for a property which we define and which we call Pareto-Optimality. Okay, so Pareto-Optimality is sort of this property that comes out of this partial ordering over learning algorithms. So if you compare any 2 learning algorithms, A and B, there are 3 possible words. And the comparison we are doing is over the set of all possible optimizer payoffs. Right? So these square boxes are sort of noting, so you look at every possible optimizer, you look at the payoffs that each of these algorithms get and you're comparing these 2 numbers. So if you look at the first world, you can see that algorithm A does just as well as algorithm B against every possible optimizer, and in fact does strictly better against some non-trivial set of optimizers. In other words, that picture, if it's indeed the truth of the world, is telling you that when someone offers you algorithm B, you should just say that, you know what, I might as well just play algorithm A instead. And we call this property Pareto domination, and say that, you know, algorithm A is in some sense a no-brainer to play rather than algorithm B.
Just a clarification question. So when you say different optimizer, you mean they have different utility functions,
Yeah,
but they still they do best response?
They do best response. So depending on the utility function, their best responses are going to be completely different as well. So you're comparing different transcripts, absolutely. Pareto optimality is what we are looking for. It's just the absence of Pareto domination. All of these definitions are robust, by the way. Like any reasonable definition of robustness you can think of, like the differences are not sublinear, the differences are linear, the limit averages, everything's happening, they're hiding on the math. Okay, so I'm going to quickly tell you about the main results of our paper. So first of all, it's a negative result, which says that not all no regret algorithms are Pareto optimal. Some of them are in fact Pareto dominated. And the usual heroes of like multiplicative weights, FDRL, all these algorithms, we are telling you that there is good reason not to play them in games where you know your own payoff, because there is a no-brainer reason to just do something else instead. And it's based upon like understanding best responses to these algorithms. However, there are algorithms which are Pareto optimal and no regret. Coincidentally, given the session, the set of any no swap regret algorithm will satisfy this property. By the way, this is not the last word on no regret algorithms. So if you have your favorite no regret algorithm that does not fall into one of these categories, come talk to us. We can tell you something interesting. Okay, I'm going to hand over to Natalie, who's going to tell us about some interesting geometric tools that we use for this problem.
Excellent. We are going to skip past this related work for now, just in time. But there are many people in this room who have worked on things that are related to this problem, and we're built on the back of giants here, and we're very happy to talk about the connections after the talk. Great. Okay, so for the rest of the talk, now that Eshwar has done an excellent job, introducing this problem, I'm going to talk about this one very useful tool that we utilize in order to make progress in it. And then, because this is a no stop or get session, I will give a partial intuition for a very small part of the proof that no stop or get is Pareto-Optimal. We are again very happy to talk about this more offline. Okay, so let's start to think about how we might achieve. So, and by the way, what's this object? It's menu. So watch for that to come up again. We're going to talk about menus. Okay, how might one think about achieving no regret and Pareto-Optimality? Well, what information do you need to keep track of to even check if you have done this for some particular strategic interaction, right? Well, we need to know what the learner payoff was, what the optimizer payoff was, right, to make sure they're best responding, and we have to know the learner regret to make sure we're playing a no regret algorithm. So to do that, one thing we could do is we could look at the entire transfer play, right, which is just a sequence of action pairs, right? That's nice, but it's a huge object. So I'm going to propose a simpler, more succinct statistic that will still capture all these things. Correlated strategy profile. So the correlated strategy profile is, so imagine that transcript we just talked about. I'm going to smush it down an average over all time steps t. And it's going to be an empirical distribution over all resulting pure action pairs. So here, when I talk about pure action pairs, I'm really talking about not just the fractional, but like in the actual base game, you know, you can always decompose over time and over the distribution each round to just like one distribution over these pure action pairs. Okay, so this is independent of t now. Yes.
What's the circle X symbol?
Oh yes, this is the product distribution. That's a great question. Yeah. Okay, so we need to track information about these things, and it turns out that this correlated strategy profile still contains all the information to figure out these three things. Okay, interesting. And those of you who are familiar with this, CSPs are in the same space as the objects of correlated equilibria. Okay, so let me give an example of a CSP to some sequence. Say the learner's algorithm is, I'm going to mimic the optimizer. And they're playing some rock, paper, scissors game. And the optimizer decides, what I'm going to do is I'm going to play paper, rock, paper, rock. So then, of course, the learner, you know, after the first round, will play, like, they'll mimic what happened the last round. So what is the CSP of this? Well, it's just half the time the learner plays rock, the optimizer plays paper. Half the time the learner plays paper and the optimizer plays rock. Wonderful. Okay, coolio. So let's pause for a moment and ask, okay, so what correlated strategy profiles are possible to induce against some algorithm A? The answer is a menu. This is the space that we're looking at. So for some algorithm A, you know, you could have some optimizer. They don't even have to be best responding anymore. They could play any sequence of actions against this. And this is going to result in some correlated strategy profile. If we take the convex hull over this entire correlated strategy profile of the entire ones that can be induced, this is going to be the menu of our algorithm. So note that this is an n dimensional simplex because this correlated strategy profile, right, is itself a distribution over nm objects, where n is the number of actions of the learner and m is of the optimizer. Okay, so let's just give a very brief example, a simple example to make sure we're all on the same page. So let's say I had this super simple learning algorithm. I'm the learner, I could play P or Q, optimizer could play A and B. We don't care about the utilities here. I'm just always going to play P. Okay, what is the menu here? Okay, so it's very simple, right? So there's no Q's in here because the learner's not given the opportunity for Q, but the optimizer can play A and B whenever they want at any time. So the menu is just the convex combination, the convex hull of A with P and B with P. Okay, does that make sense? Great. Okay, so the great thing about menus, right, is as I mentioned, so basically every point in this is just a linear combination of the pure strategy move pairs of the game. So the optimizer's utility, whatever it is linear in this space. So it's a very complicated question that we think about a lot in our work and have some interesting results on how exactly this optimizer will best respond in an algorithm space. But to think about what point is achieved in this menu, we're able to bypass it here and say, what happens? So whatever they do to get this, the thing that's going to happen is they will play some sequence that ends up with them selecting the extreme point of this menu in the direction of their utility vector. Okay, and this also tells us what utility the learner gets, right? Because the learner's utility is also linear in this space. Okay, this now also allows us to reason about comparing two algorithms under the same utility of the optimizer, right? We can look at these two menus, and now obviously the dimensions are much higher, but I promise this intuition does map to higher dimensions. And we can see here, okay, under the same utility vector of the optimizer, in algorithm 1, it's this point's picked, in algorithm 2, it's this point. And so actually in this case, you really would have rather played algorithm 2, which by the way, is a certificate that algorithm 1 cannot Pareto dominate algorithm 2, right? This is an instance where algorithm 2 does better. Okay, so a key insight in our work is using these menus to be able to then prove geometric properties, which will translate into proving results about algorithms themselves. Okay, so I don't have time to do too much of the proof, but I'm just going to tell you one interesting thing, which is we have this nice result that all no-swap regret algorithms are Pareto-optimal. And one reason that we're able to say that so strongly is because we're able to just prove that about one menu, because all no-swap regret algorithms actually have the same menu. So how do we go about thinking about that? So let's think about this object, which I'm calling MNSR. It is the convex hull of all no-swap regret correlated strategy profiles. So just like you can check whether or not a correlated strategy profile exhibits external regret, you can also check whether it exhibits swap regret by saying, all the times in this move pair that we have this side, would you like to switch to something else, right? Okay, so this is like some object, like we don't even necessarily have to reason about like much about it in order to say, well, one thing that's definitely true is every no swap regret menu, so every menu of no swap regret algorithm must be strictly contained within it, right? Because otherwise you're saying I could play against this no swap regret algorithm and induce some correlated strategy profile exhibiting swap regret, right? And that's like the whole promise is that that's not possible, right? Okay. But actually MNSR is inclusion minimal, which means that there are no valid menus strictly contained within this object I mentioned, which means that the menu of any no swap regret algorithm has to be exactly MNSR. Okay, so this is particularly interesting, yes.
Did you say why MNSR is inclusion minimal or?
No, but I'm happy to talk about it offline. Yes, this is particularly interesting in the light of recent results, new papers that have different ways of getting no swap regret, which also happy to talk about offline, should have added a link here. Okay, finally, I'll leave you with one point, which is even if you don't care about Pareto-optimality, which we think you should, we still think you should care about menus because they provide a new framework for reasoning about algorithms. So in this work, we think about algorithms and we think about what their menus are in order to analyze them. But we also think that you could go from menus to algorithms in a new paradigm of algorithm design. So instead of starting with, oh, what is the algorithm and what does it achieve? You can start with, what are the things that I want to be possible to achieve against any best responding optimizer? And as long as this is a feasible set, which all menus are, as long as this is an approachable set, then there is an algorithm that is like you can automatically say is going to achieve this menu, which is you could run a Blackwell approachability algorithm over this set. So you can start with a menu and you can come up with an algorithm. And some of this is really useful in some of our follow-up work that we're doing is thinking about menus in this way. Cool. This is just, the combination of also everything in this box, not just these top two is filled, like you can have any combination of regret and Pareto-optimality. Yeah, and that's it. Thank you so much.